Hello everyone. Welcome to First Online University, a global platform for all your education and growth related needs. In this lecture, we are going to start with a new topic that is chemical kinetics. Now, kinetics is related to motion. Okay, it's related to time, it's related to rate. Okay, so if there is a particular chemical reaction taking place, how fast the reaction occurs, what time is it taking to complete the reaction, that is to deal with the kinetics of that chemical reaction. So we call it as chemical kinetics. In this lecture, we will be focusing on the introduction part to chemical kinetics, and from next lecture onwards, we will dwell deeper into the concept of chemical kinetics. We will start looking at the various orders of reaction, rates of reaction, various types of reaction. Before we begin, a piece of information for you. You can use the coupon codes mission JEE or mission NEET while you enroll at First Online University for mission JEE or NEET. Let us start with the introduction to chemical kinetics. Now, whenever there is a chemical reaction taking place, now this is something like a vigorous chemical reaction that has been shown, but in general, any chemical reaction taking place is going to depend on three factors. Feasibility, that is how easily the reaction can take place, and that is the concept which is answered by the branch of science called thermodynamics, that is chemical thermodynamics. Then the extent to which the reaction will take place, whether it will go to completion or is it going to stop in between, that is given by chemical equilibrium branch of chemistry. And when we talk about the speed of reaction or the rate of reaction, that is given by chemical kinetics. Okay, so you can always remember this car that has been shown to you. The speed with which the car is going to run is nothing but the kinetics of the car. And when we talk about a chemical reaction, the speed with which a chemical reaction would take place is known as chemical kinetics. The Greek word kinesis means movement. So therefore, it is the branch of chemistry which deals with the study of reaction rates, not only the speed or the rates of reaction, but also the mechanism of reaction. Let us see an MCQ. Chemical kinetics deals with the dash of reaction. Spontaneity? No, that is thermodynamics. Rate? Yes. Extent? That's chemical equilibrium. None of these. So option B is the right answer. Now, what are the various types of reactions? There can be various types of reaction. A reaction could be a very fast reaction, a slow reaction, a moderate reaction. Now, when I say a very fast reaction means that this reaction takes place within microseconds or it takes place very instantaneously. Means we just, add the components and we quickly get the product. We do not even get to know what is happening while the reaction is actually happening. It's only later that we can calculate things or, mechanisms can be found out. It's always later, not during the reaction. These include all the ionic reactions, that is reactions involving basically the ions reacting with each other, then all the precipitation reactions, all the neutralization reactions, and all the combustion reactions. For example, precipitation of AgCl, that is silver chloride, by mixing aqueous solutions of silver nitrate, AgNO3, and NaCl, sodium fluoride. So AgNO3 plus NaCl will give me AgCl white PPT plus NaNO3 is going to be formed. So if you see that you have NaCl solution in the test tube, okay, that is colorless because NaCl is completely soluble in water. The common salt, if you take water in a glass and you add salt to it and you mix it, do you see anything, like particles or something like that? No, because it's like completely soluble in water. The moment I add AgNO3 solution to the test tube containing NaCl, you will see the moment a drop of AgNO3 enters into the solution, you will have a white curdy precipitate as it has been shown in the picture. So this is a very instantaneous or very spontaneous or very fast reaction. Next is a very slow reaction. Now, these reactions could take days, months, or even years. For example, rusting of iron. We all know that iron objects do get rusted, but that's a very, very slow process. Okay, it's like when you buy a new house. Okay, all the material inside that has been the water pipelines or anything that is made up of iron will stay as such for 20 to 25 years. But it is only after these many years that you will have problems of some leakage taking place behind the walls, because the plumber would come and he will say, okay, there is some leakage in the pipe because the pipe has been corroded or rusted and needs to be changed, it needs to be repaired. Okay, so that 20 to 25 years is a very long period, which means that rusting that is taking place is a very slow reaction. That is, iron will react with oxygen in the presence of moisture to give ferric hydroxide. Next is moderate reaction. Now, the reactions which are neither very fast nor slow, but they take place at a moderate rate or speed. For example, decomposition of hydrogen peroxide, that is decomposition of H2O2. So H2O2 will get decomposed to give water and oxygen is going to be liberated. This is how you can visualize the reaction taking place, that is H2O2 decomposes to give water and O2. Or the inversion of cane sugar to give glucose and fructose. So that is C12H22O11 sucrose reacting with water to give C6H12O6 and C6H12O6, but one is glucose, the other is fructose. So this is also a moderate reaction, neither very fast nor very slow. Another example could be decomposition of nitrogen pentoxide. So what happens is N2O5, that is nitrogen pentoxide, is going to decompose to give NO2 and O2 is going to be liberated. Now, in chemical kinetics, we are mainly going to study the moderate speed reactions only, because it's easier for us to find out the properties or the kinetics associated with a moderate speed reaction as compared to a very fast reaction, which is very difficult to monitor, or a very slow reaction, which takes a lot of time to get completed. And we cannot really wait for any such reaction to get completed and then we, work on its kinetics. So it's always better that we, study moderate reactions. See, we always have a habit of being diplomatic. Okay, someone asks you something and you do not want to answer. You'll say, yeah, that's fine. So now that does not show whether you are with it or you are not with it. That's diplomatic. That's what is chemical kinetics dealing with. Okay, so very similar to you. Okay, let us do a question here. The enthalpies of formation of alumina, that is Al2O3 and B2O3, are minus 1676 and 1274 kilojoules per mole respectively. Can this data help us to know the rate of oxidation of aluminium and boron? Think what enthalpies relate to and what chemical kinetics is about. The answer is no, because enthalpy is a thermodynamic data and thermodynamics is not about the rate of reaction. Okay, thermodynamics is about the feasibility of a reaction. Let us solve an MCQ. Which of the following reactions occurs most rapidly at room temperature? H2 with combining with O2 to give water, H plus plus OH minus giving water, sucrose in the presence of concentrated H2SO4 giving 12 carbon plus 11 H2O, or 2NO combining with O2 to give NO2. See, what you all had to remember was the examples of reactions which are very fast: precipitation reaction, neutralization reaction. So where do you see neutralization reaction? Option B. Therefore, that's the correct answer. Second question is, the speed of the reaction can be moderate. Yes. Very fast. Yes. Very slow. Yes. So all of the above is the right answer. Third question is, chemical kinetics deals with those reactions which occur at slow speed. No, I told you, like you, chemical kinetics is also diplomatic. Moderate speed, yes. Fast speed, no. All of these, no. So option B is the right answer. See, some of you who would not have listened carefully to what I just spoke in the previous 3-4 slides, you will say all of these is the right answer. See, there is a difference between all of these being the right answer to this question and otherwise. See, there are reactions having slow, fast, or moderate speeds, but that is not the question here. The question here is chemical kinetics can be used to deal with what kind of reactions? So that is only the moderate reactions. Next, we study what is the rate or speed or velocity of a reaction. Now, there are two things whenever we talk about any chemical reaction. One is the reactants, the other is the product. Right. So suppose we sit in a car and, when we are just starting to go somewhere, which is our destination, we are the reactants at that time. Now, the speed with which the car can go from its place of its origin, that is so the speed with which our car takes us from our home to supposedly, our friend's home. So the speed is basically expressed by distance upon time. That is change in position upon time. Similarly, when we talk about a chemical reaction, we define the rate or speed or velocity of chemical reaction as rate being equal to change in concentration divided by time taken. Okay, so this change in concentration is in the numerator. So as we are going from the reactant to the product, okay, since we cannot define as to what position is getting changed, we will be defining in terms of the concentration. So the change in concentration divided by the time taken will give me the rate of reaction. How do we define a rate of reaction? A rate of reaction may be defined as the change in concentration of any one of the reactants or products per unit time. So we do not have to take into consideration all the reactants and all the products. See, how this is working is, suppose you, your mom, your dad, and your sibling, all four are going to a cousin's house, maybe your maternal uncle's house. Okay. So what will happen is that all four of you are going to sit in a car. All right. And then that car collectively is going to take you all four to your cousin's place. So the speed with which you have reached, or the rate at which you have reached, can be defined by taking speed of any one of you. Okay, it could be you, your mom, your dad, or your sibling. We need not have, speeds multiplied, and, nothing is important at that time because all four of you were together there, right? Starting from your place to your destination. So the time in which, or the rate at which you reached your destination, can be defined by any one of your speeds, right? Similar is the case here. Any one of the reactant or any one of the product, when we take its concentration per unit time, that gives me the rate of that reaction. Now, how do we represent the rate of reaction? So if we have a reactant going from the reactant side to the product side, okay, so there are some reactants involved and they're going to get converted into products in the presence of defined conditions, then there are various ways of representing the rate of reaction. Now, since we know that the rate of reaction can be expressed in terms of concentration of the reactant, any one of the reactant, or any one of the product. So, and the reactants are disappearing. In any chemical reaction, the reactants would disappear and the products would appear. Agreed? So, the rate of disappearance of reactants will be equal to the rate of appearance of products. So, the rate of disappearance of reactants is rate of reaction is equal to decrease in the concentration of reactant, because reactant concentration is going to decrease because it is disappearing, divided by the time taken. That is also equal to, so supposedly, if we are talking of the rate of reaction in terms of the rate of disappearance of the reactants, then the rate of reaction will be equal to decrease in concentration of the reactant divided by the time taken. Now, let us say that there are two reactants, R1 and R2, with concentrations given by R1 and R2 as it has been shown, and they take time T1 and T2 to get converted into the products. So the total time taken would be T2 minus T1, right? And the change in time would be T2 minus T1, change in concentration would be R2 minus R1. So change in concentration means decrease in concentration. So supposedly we take, suppose initial time was say at 12 we start the reaction and the reaction ends at 12:02. Okay, so 12:02 minus 12 is going to give me the time in which the reaction has taken place, that is delta T, and whatever the initial concentration of the reactant was. So R1 is the initial concentration of reactant, R2 is the, sorry, I'm so sorry, I said it wrongly initially. R1 and R2 are not two different reactants. R1 was the initial concentration, R2 is the final concentration of the reactant once the reaction has taken place. T1 is the time, that is where we have started the reaction, and T2 is the time at which we are going to observe the reaction completion. So the change in time or the time taken is T2 minus T1, as I've given you the example 12 to 12:02. So delta T is going to give me the time taken, and decrease in the concentration. Since we know that, the concentration is going to decrease. So when we do R2 minus R1, that is, firstly, if the concentration was 10 molars and it is reduced to 2 molars, so 2 minus 10 is going to give me an answer of minus 8. Therefore, this decrease is going to be given by a negative sign, that is minus delta R upon delta T, right? Next, we can also have the rate of appearance of products as the rate of reaction. So rate of reaction would be the increase in the concentration of product, right? Because the product is increasing in concentration divided by the time taken. So if P1 is the initial concentration and T1 is the initial time and P2 is the final concentration and T2 is the time at which we are stopping the reaction to observe how much of it has been completed. So increase in concentration, or the change in time, again, that is time taken, would be T2 minus T1. And here P2 is greater than P1, that is final concentration of the product is greater than the initial concentration of the product, because product is being formed in the reaction. Therefore, delta P, that is P2 minus P1, is going to be a positive quantity. Therefore, we can write the rate of reaction to be delta P upon delta T with a positive sign. So rate of reaction is minus delta R upon delta T, which is also equal to plus delta P upon delta T. So this is the important rate equation that you need to remember. Next is graphical representation. If we have the reactant concentration versus the time, we know that with the increase in time, or as the reaction proceeds, as the time increases, the reactant concentration is going to decrease. But if we have the product concentration versus time, with the increase in time, the product concentration is going to increase. But that is going to be up to a certain extent that it will increase, and then it will remain constant with the increase in time, because there is no more reactant left to form more products. So this is how we can combine the two graphs to give me concentration versus time graph. So reactant concentration decreases with increasing time and product concentration increases with increasing time. Initially, so the reactant concentration will be non-zero, but the product concentration will be zero initially because no product has been formed. If I talk about, so this was concentration versus time. If I talk about the rate of reaction versus time, so see, there are two types of reactions. One is forward reaction, that is reactant to product side. The other is backward reaction, that is product to reactant side. So if it's a reversible reaction, once all of the reactants have been consumed and in an equilibrium reaction, the product concentration increases, then according to Le-Chatelier's principle, the reaction will start going back into the reactant side, towards the reactant side. So this is going to be the rate depending upon the concentration of the reactant. So if we initially take only the forward reaction, okay, then initially the rate of reaction will be very high because the reactant concentration is very high. As the reactant concentration goes on decreasing, the rate of, see, it's very simple. When you have a lot of energy in you and you are asked to, you know, take 5 rounds of the ground, okay, of the playground. So initially you're very full of energy and you're just going to take the first round very fast. Then in the second round, since you've lost some amount of energy, your speed will be slow. In the third round, it will be slower. The fourth round becomes difficult for you to complete. And the fifth round, you're not even able to do it. Why is that so? Your energy is nothing, your energy is nothing but the concentration of the reactant. So as the concentration of the reactant goes on decreasing, the rate of the reaction will also go on decreasing with time. Now, what are the units of rate of reaction? Units are concentration upon time, right? So it would be molar per second or moles per liter per second. One is the same thing. Moles per liter per minute, moles per decimeter cube per minute. So anything you can write. Now, in the gaseous reaction, the units will be partial pressure. In the gaseous reaction, we cannot take the concentration, okay? When we have reactants in the gaseous form or the products also being formed in the gaseous form, then we cannot really take the concentration terms. We will have to consider the partial pressure terms, that is the pressure of each of the reactants in each of the products expressed in terms of partial pressure. So that would be equal to partial pressure upon time. So that will have the units atm per second. Now, let us have a look at a few MCQs. Units of rate of reaction involving gases can be expressed as moles, no. Moles per liter per second, no. ATM per second, that is atmosphere per second, or all of these. Option C is the right answer. We are not talking about any general reaction. We are talking about a very specific reaction that is involving gases. And the moment gases comes into picture, we cannot talk about concentration. We will talk about pressure. And pressure has the units atmosphere. Next question is concentration of reactant dash with time. So we know that reactants are getting consumed, so their concentration is going to decrease, and therefore option B is the right answer. Last question is concentration of the product dash with time. Since the products are going to be formed, so their concentration will increase. So option B is the right answer. So this is all about the introduction to chemical kinetics chapter. I hope you found it interesting because this chapter is actually very interesting to, because it's something very new to you. This is something that you've not really learned anywhere in the, in your lower classes, in your lower standards, and this is something new and very interesting, and it's also going to be numerical based, so you'll find it even more interesting there. We'll continue with greater details of this chapter in the next lecture. You can subscribe to our YouTube channel for joining YouTube live classes for best NEET or JEE coaching. You can also download the First Online University mobile app for continuous learning through your smartphones. Keep learning with First Online University, a team of millions of learners and educators worldwide.